Hi everyone, my guest today is Professor David Kaiser. He is a professor of physics and history of science at MIT, and he is an expert on quantum mechanics. He actually wrote a book called How the Hippies Saved Physics, which is about the history of quantum mechanics in the 60s and 70s. So a very good person to ask some of the fundamental questions on quantum mechanics. So let me start with something very basic. Why is quantum mechanics so weird?
It's a great question. A phrase I always come back to is that quantum theory seems to insult our intuitions. It not only does it not make sense, it almost feels like it's sort of especially counterintuitive, at least in some of its aspects. Why is that so? I guess we could speculate that, we grew up as people, both individuals and as a long-term history of our species, worried about things on the scale of this table. We have to worry about things that are, a couple feet, a meter across. And a lot of the especially strange features of quantum theory, as we've come to learn about them in the last almost 100 years or so, they show up not when we think about, say, this table or aircraft or even, sending probes out into space. They really seem to show up when we look at really small things. We look at atoms or pieces of atoms. And so partly why I think it's so strange for many of us is because in our everyday world, kind of getting up and doing our things, we don't trip on these aspects of say wave-particle duality or Schrödinger's cat. These are things that we're confronted with when we try to make sense of very specific experiments or make sense of some of the really quite beautiful mathematics that the community's developed over 100 years. But we have to work to even find the weirdness.
Yes, that's a very good point. And so do you think that was what worried Einstein?
Einstein, I think, had many worries. He was, he was a worried guy. He was an anxious guy. I think the biggest concern that Albert Einstein had with quantum theory, which again we should remember, that Einstein was really a fantastic architect of quantum theory, and I mean one after another, the things that we now take for granted the building blocks of this edifice came from Einstein and from Einstein alone in the early days. So he didn't. It's not like he was automatically a detractor, right? Nonetheless, it's true that he certainly turned his attentions away from quantum theory because he didn't think it was the best place to stop. He thought these were interesting regularities that matched experience and experiment, but he thought it would be selling short if physicists didn't keep working to find what he considered a kind of more ultimate, deeper explanation for these things. So Einstein, it's not that he thought quantum mechanics got things wrong. He was always quick to say it matches experiments, including very ingenious, strange experiments. It matched the data quantitatively very well, but it wasn't solid enough for him. It wasn't a foundation on which to keep building. And he came to consider, especially later in his life, that it was really a kind of cop-out to stop with the strangenesses that had come on Earth, some of which he helped to actually clarify himself, because it wasn't what the job of the physicist should be. It really was like quitting early on your job. It was almost a moral concern he had, that physicists had a responsibility to try to understand nature according to certain very broad and very reasonable sounding assumptions or ideas, things that had driven him to extraordinary success exploring things like relativity, the motion of objects when they move very, very quickly, or when masses become really condensed and glommed together, so we have to worry about the warping of space and time themselves. Principles that Einstein had literally built his career on, and that quantum theory showed more and more divergence from. So Einstein, I think, was worried that this was an interesting scaffold, but it should be a hint to press further. He said we were just stopping too short.
And how do you contrast that with Bohr's position?
So Bohr is another, fascinating deep thinker, one of the great, again, architects of the world in which we now live. Both Bohr and Einstein were tremendously influenced by philosophy as young people, as students and even as young physicists themselves. They just were influenced by different philosophers in part. And so Bohr was in some sense excited. He was actually eager to explore what he considered the general epistemological lesson of the quantum. That's his favorite phrase. He thought this is showing us about new philosophies to explore rather than departures from safe ground. So Bohr was in some sense almost giddy with these new intellectual philosophical possibilities. And he really cultivated around him a circle of people who thought their job was to pursue the interpretation of that stuff as much as the equations, the experiments, the data.
So sometimes I think that, in a sense, Einstein was a victim of his own success. Because if you think about it historically, right? So when Einstein came into the picture, there was Newton's gravity. And Newton's gravity had something really weird about it, which is a spooky action at a distance, in a sense that, you know, you have the sun and you have the earth, and the sun makes the earth go around with this invisible force of gravity that seems to act instantaneously without any touching. And what he does with that is he sort of exercises that ghost, right, with his general theory of relativity, showing that actually that's not quite what's going on. That is a very superficial interpretation. What you really have is this curvature of space that actually can explain gravity in a much more direct way without that spooky action at a distance. And then he encounters quantum mechanics, and something weird goes on.
A number of weird things, and one of them that he really put his finger on, and we still credit it's the Einstein-Podolsky-Rosen, or EPR paradox. Einstein was central to this in the mid-1930s, was exactly to show that quantum mechanics seems to require the kind of spooky action at a distance that Einstein had thought he'd gotten rid of. In fact, it was Einstein who coined the phrase spooky action at a distance in a letter to his friend Max Born, the Nobel laureate. And this was not meant to be praise. He was making fun of Born and Bohr and Heisenberg and the whole gang who were following on this quantum mechanics road. So Einstein again said, you know, if that's what you believe, then you're out of your mind. This sounds like, you know, witchcraft or all the things we've worked so hard to get rid of. So what was Einstein putting his fingers on? He had this amazing intuition that the equations of quantum theories, as they've been worked out partly by himself and by people like Werner Heisenberg and Erwin Schrödinger and Niels Bohr and others, that they have this strange feature where certain kinds of objects, certain particles, little bits of matter, if they're prepared in a special way, they should retain a kind of link, even if the particles move arbitrarily far apart. And that it's that distance that starts to worry Einstein. The whole game for relativity to Einstein, just as you were saying before, is that physical influences should move point by point. There should be what he would call local interactions. Something pushes up here and that pushes the next thing over and so on. Nothing should be happening instantaneously with nothing in between, with no physical connection in between. So thought Einstein. And yet he and his younger colleagues, Podolsky and Rosen, realized that if we take quantum mechanics at face value, there should be this very strange connection across arbitrary distances. It seems to act instantaneously, all the things he was worried about, where if one prepares these particles, they move far apart, and one can choose to make some measurements on particle A, let's say, and at least as far as they were concerned, that seemed to instantly change the behavior of particle B, even if particle B were on Alpha Centauri, or, you know, the furthest edge of the cosmos. And furthermore, it looked like that influence should somehow move sort of out of space and time. It should be totally instantaneous. And that was exactly what Einstein had worked so hard to expunge.
And of course, this was 1935, right? And a lot has happened since, and now people are making experiments to test this so-called spooky action at distance.
Yes.
So can you give us a bit of an overview of what's going on that?
Sure. It's a wonderful, rich story, and it extends the better part of a century, and even in this sort of uptick of activity is still a 50-year-old story. So after Einstein had died, after Niels Bohr had died, neither having satisfied the other with their good-natured but intense debates, another very, very bright physicist named John Bell came along, who realized that what had kept these titans up at night, Einstein and Bohr, arguing and sort of throwing out thought experiments to try to catch each other in a mistake, Bell realized this stuff might be more than just the stuff of late-night discussions. It might be testable in a laboratory. One could actually produce pairs of particles, and one could imagine conducting measurements on one and looking at correlations of what happens with the other across some distance. And so John Bell introduced in 1964 something we now call Bell's theorem, or Bell's inequality, which was quantifying exactly how much this spooky action should hold in the world if the world is described by quantum mechanics. Bell himself was holding out for an answer more like Einstein. So Bell hoped quantum mechanics would fail. He said, let's do an experiment and show this is wrong. And I don't know if it was quite to his chagrin, but maybe to his surprise, when the experiments really were done starting in the 1970s, every single published experiment has shown the results exactly in line with quantum mechanics, showing these correlations at a distance, violating a bound that Bell had derived if the world obeyed the kind of rules or assumptions that Einstein had believed in so strongly. And so there's been this more than 40 years of experimentation in increasingly clever, ingenious, sometimes kind of Rube Goldberg sort of ways to subject pairs or sometimes triplets of particles to these kind of coordinated questions. Even when the particles are so far away their answers can't line up, there's no local explanation for how the answers could line up. And every single time the answers, we ask a question of particle A, ask a distinct question of particle B, and the answers line up even though the particles had stopped interacting long ago. And that's exactly as quantum mechanics predicts. It's this strange notion called quantum entanglement. And it just flies in the face of the kind of universe Einstein thought we lived in.
So spooky action at a distance prevails in the quantum level.
It certainly has been shown time and time again to hold up in very clever experiments. One of the great questions is, where does that go? How big an object or pairs of objects could you entangle and retain that special quantum behavior? I mean, objects in our ordinary world don't do that, right? Baseballs thrown in opposite directions don't show these amazing correlations. Even the axles of spinning tires, the measurements on them aren't correlated nearly so much as they are on these little bitty bits of matter, according to quantum theory. So the question, a great challenge, is how big a thing made of quantum stuff could one make, or pairs of things, and still show that quantum action at a distance? And I believe people have gotten to, big on the quantum scale, molecules, say, many, many times bigger than electrons, single little bits of atoms, but still exponentially smaller than you or me or cats or baseballs.
I heard there are plans to try to do that. They've done it with buckyballs, which are like a 60 carbon atom ball of a molecule. Yep. And it worked, right? Yep. And I heard they're trying to do it with a virus.
I've heard about viruses, yes, that's right.
And then if you go from there to bacteria, then there'll be a very interesting conversation, which is, how does life respond to entanglement?
That's right.
Or is life a completely classical phenomenon, or does it have any quantum mechanics into it?
And even before we get there, which are amazing questions, if you can do it with a bacterium, I mean, some bacteria are visible with the naked eye. We can get to things that one could actually see and have them obeying the laws of quantum mechanics, not just these sort of impossibly small little bits of matter like electrons, which we know we can't sort of see with our usual senses. So it's this challenge of sort of scaling up the quantum weirdness. When does the quantum weirdness kind of fade away and the world that obeys laws more like Einstein's and ultimately like Newton's, when does that world emerge? And that's an ongoing challenge.
Yeah, so that is the transition from quantum to classical. Like, we perceive reality in a very classical way, and yet if you go down to very small scales, everything seems to be quantum mechanical and obeying laws and behaviors which are so different. And John Bell, that you mentioned before, he had an essay called The Speakable and the Unspeakable in Quantum Mechanics, right? And his idea was, how many atoms do you need to put into something for that something to start to behave classically? So where's the boundary, right? And there is this thing called decoherence that seems to help us understanding a little bit of that. So what is decoherence?
It's a great point. And so decoherence has many sort of great, strong proponents, and it's an amazing advance in our understanding of exactly this question of the kind of quantum to classical transition. And roughly speaking, as I understand it, decoherence says that these quantum systems that have this special quantum behavior, they don't exist, or they needn't exist only in a vacuum, and in fact they can be interacting with sort of their environment all the time in ways that we hadn't necessarily taken into account before. And could the constant little jostlings and interactions with the other little bits in the environment, could that reduce this kind of proliferation of possibilities? Quantum mechanics is all about calculating probabilities instead of definite outcomes. Could the constant jostlings and scatterings with other little things in the environment, could that actually be sort of winnowing the quantum possibilities down to one main kind of road that we then see emerging that we would have considered just the world, just the classical description? So in a sense, it's suggesting, had we not taken seriously enough the role of interactions, in some sense it's trying to repeat, I think it's drawing inspiration from a great lesson physicists had learned 100 years earlier, in the end of the 19th century, about trying to understand matter in bulk? What happens? I mean, why does this table behave the way it does if it's actually made up of tons and tons and tons, gajillions of independent atoms and molecules? There can be bulk properties that emerge when we take into account the kind of large numbers of things in interaction. And I think decoherence is in some sense trying to apply that lesson to the quantum world. And some people say we've got it, that's the answer. Others will say, well, but there are other things left still open. And so it remains a matter of ongoing research.
So the other weird or interesting aspect of quantum mechanics is that it sort of blurs the distinction between observer and observed, right? In the classical world, it's very clear that this is the table and this is me and I'm not the table and we're separate. But in quantum mechanics, that's not quite true anymore, right? There is a relationship between the act of observing and the physical properties of what's being observed.
And that's another topic that will excite the passions. If you want to get a bunch of physicists, all riled up, lock them in a room and say, discuss this question. So, but it's true. So certainly, according to Niels Bohr's main line of thought, and Bohr really set the stage for these discussions decades ago. Bohr really was troubled by this lack of a clean separation, just as you described. Heisenberg, in his first gropings toward what becomes known as the uncertainty principle, was really worried that we sort of clumsy humans are messing up the quantum world, that we can never get a sharp response to certain kinds of questions because we've interacted, we have kind of put ourselves clumsily into our own experiment. And then other physicists years later would come along and say, well, that might be true for some instances, but is that really getting at something basic and fundamental about nature? After all, we're just bags of atoms as well, right? Why make this sharp distinction between observer and observed that Bohr still wanted to maintain? And so others will say, well, maybe there's no so-called measurement problem. Maybe there's no moment when an observer steps in and forces a quantum system to make one decision, choose outcome A or B. Maybe the universe chooses both, but we only are noticing one of them because we're on some part of some larger kind of quantum realm of possibilities, that everything looks perfectly self-consistent to us, even though there might be a nearly exact copy of us that sees the other outcome somewhere in some sort of disconnected part of the universe. And so this gives rise to something called the many worlds interpretation, which again sounds, to my mind, even more like science fiction than Niels Bohr's approach. And yet I think if you took a spot poll today, I bet you'd find more physicists who would vote for many worlds than for the kind of classic Copenhagen or Niels Bohr line, which to my mind is a sign of just how hard this question remains.
So now we're talking about the interpretation of quantum mechanics, right? Which is, of course, a completely open question. And as you said, you get passions excited very quickly because people are going to have different ideas. You may ask, some people may say that many worlds is sort of a crazy idea because if the universe is splitting into different options every time we make a measurement, where are all these other options? Right. And if we can't see them or interact with them, how do you know that exists, right? And is that physics or is that metaphysics? Right. And so it seems to me that at the very core of this conversation is the fact that the equation, the master equation for quantum mechanics, depends on a quantity which is not directly a physical quantity, which is the so-called wave function, which is so very different from everything else. Yes. So maybe you can tell us a little bit how is that different from, say, a Newtonian particle moving in space?
Yeah, or even an example like waves of electricity and magnetism, like Maxwell's waves. So much of the mathematics of quantum mechanics is built upon or analogous to the mathematics that we do use to describe Newton's laws or electricity and magnetism, things with which we build the world around us. And yet with this critical difference. So mathematics has so many similarities, and yet the objects of mathematical study, of mathematical focus, really have this important difference, just as you say. So sort of the standard interpretation, or the common words to use, is that the wave function, this thing often symbolized by the Greek letter psi, looks like a pitchfork, that psi is not necessarily a thing in the world, but it's a statement about probabilities of what could happen in the world. And that even saying that sentence actually has now become a bit more controversial than it was
Right.
before
So
too long
that's an
ago.
ontological state.
That's an ontological state. Or I guess it's saying, is psi only epistemic? Does psi only represent our knowledge of what things could happen? Right. Or is psi a part of the furniture of the universe? Is psi, is the wave function, as real a physical object as, say, the electromagnetic field is? And there are remarkable experiments being done now to try to pin that question down, just as John Bell tried to pin down questions about quantum entanglement with experiments. So I'd say my sense is the jury's still out. Both of those two sides have very smart and very well-spoken proponents. But what I find amazing when I step back and put my historian's cap back on is that that's a question that in some sense goes back 90 years. This is the 90th anniversary now. In 2016, it's the 90th anniversary of Erwin Schrödinger's introduction of the wave function and of the equation that it would obey. And of Max Born's interpretation that psi is telling us about probabilities for things to happen. And for 90 years, we've been writing down the same equation and arguing about what it means. For almost 100, and these are smart folks working very hard. It's not this is an occasional question people think about. This has consumed a community of really millions of people, I think, if we add up all the people who've worked on this steadily for almost a century. And we can still get people arguing, with great passion today.
And Schrödinger himself, right? I mean, 1935, the same year that Einstein, Podolsky, Rosen wrote their paper, he wrote his paper on the Schrödinger's cat.
Yes.
Which was really trying to ridicule his own theory in a sense, right? So what's the deal with the Schrödinger cat?
Schrödinger and Einstein were kind of contemporaries. They were both a bit older by the time they were working on this than many of the young guard, Werner Heisenberg, Wolfgang Pauli, and some of the people who were so active. And I think Schrödinger had a sensibility much like Einstein's, at least when it came to physics, not in his personal life, different story, but when it came to physics, that the world should be described by a continuum, that we could imagine dividing, say, space into smaller and smaller parts and never hit a kind of lattice. There's just space, and it flows and laps around. And I think Schrödinger ultimately thought that this emphasis on discreteness, on quantized things, little buckets of matter, was maybe sort of pulling the wrong way, or leading to things that we might not want to have to swallow, the whole course. And so it's true, that same summer of 1935, within weeks of each other, Schrödinger published another sort of great, rich challenge to his colleagues and the proponents of quantum theory, and what came to be known as Schrödinger's cat paradox. The idea is that, very similar to what goes on in quantum entanglement, quantum theory says that at this level of sort of atoms and parts of atoms at least, the laws of quantum mechanics allow an object to be in two different states at the same time. So an atom could be, for example, or an electron could be both spin up and spin down. It could have properties that seem like they should be mutually exclusive, and yet it could somehow be in a state of both. Not either, not one or the other, just because we're ignorant of which one it is, but really a kind of hybrid of the two.
Sort of like we have a two-state shirt here. So I could have a blue shirt or a red shirt, and you could have a blue shirt or a red shirt.
Right, and quantum mechanics says sometimes we might have purple shirts. Maybe our shirts would be blue and red, either stripes or a real mixing of colors.
Or before you see one another, we could have both shirts at the same time.
Exactly. And so quantum mechanics allows for these strange, almost like ghost-like states. And so Schrödinger thought this, again, sounded just horrible. That sounds like the whole thing's gone off the rails, much like Einstein had thought. So Schrödinger wanted to dramatize for his colleagues how much one's giving up if you really believe that, how much one gives up of our understanding of the usual way the world works. So we had this brilliant sort of teasing challenge that he introduced for his colleagues. Imagine that we describe little atoms according to quantum mechanics. So far, so good. Those atoms could include a radioactive source, a source that, according to quantum mechanics, just randomly, just probabilistically spits out a certain kind of particle. We don't know when it will happen. We can say it has a likelihood to do it within, say, an hour, but we don't know when it will. We don't know which atom will. We can calculate probabilities for some kind of transition from that radioactive glob of atoms. And inside this box, we have this radioactive source. We have a detector that can tell when that radioactive source has decayed. It can't tell us when it will, but once it has, it'll tell us, oh, I just detected the products of that decay. Next to that radioactivity counter, the detector, there's a hammer that will smash down a glass of cyanide. Schrödinger clearly had a dark moment here. And the cyanide will kill a cat who's been locked inside this box. What he wanted to do is amplify this quantum weirdness that his colleagues had swallowed without too much concern at the level of atoms, and say that's just like saying the cat trapped in that box, if one follows that reasoning, must, according to quantum mechanics equations, be described as both alive and dead, at least before someone opens the box and performs a measurement, takes a look.
So those are the two states of the cat, alive
and dead. Much like our shirts could be, red. We think it'd be red and blue, red or blue. What if they were red and blue? What if the cat were alive and dead? Positions, possibilities that we would otherwise consider to be mutually exclusive. So we wanted to amplify this quantum weirdness to the scale that we live on, and say, that's really where you want to live. That's what you think, is how the world works. And again, much like with Einstein's work on what became known as quantum entanglement, Schrödinger's great genius was highlighting effects that are essential to quantum theory, that in the generations since have been tested time and time again in the laboratory, and seem sort of inescapable, at least at the level of atoms and clumps of atoms. People can make, for example, these buckyballs, as you said, these large molecules involving dozens of carbon atoms, 60 carbon atoms, and put them into these kind of Schrödinger cat-like superposition states, and measure the properties that are demonstrably different. They're experimentally, quantitatively different than assuming that sometime the molecule is in state 1 and sometimes in state 2. It really seems to be in a mixture at once, and that's strange.
So would you say that in essence, physical reality is quantum mechanical, that the classical reality that we live in is really an approximation?
It's hard to say. As you've written about and you know so well, there are a lot of big open questions, and one of them is, how do we ultimately combine quantum theory with the general theory of relativity? How do we combine our description of atoms and parts of atoms and the forces between subatomic particles, which we can calculate to extraordinary precision, compare with experiments? Is a beautiful edifice here, but it just is built on a different set of starting assumptions than this equally successful, equally flamboyant theory that Einstein gave us, the general theory of relativity, the warping of space and time. And again, in about 100 years' time, we've never been able to really knit those two together. So one might say, well, which side's going to give? Do we have to modify quantum mechanics to make it more like relativity, or do we have to modify relativity to make it more like quantum mechanics? And my strong suspicion is the prevailing opinion these days, which is different from a known fact, but the prevailing opinion is that quantum mechanics seems to be deeper, and we're going to have to find a way to make gravity, our description of gravity, look more like quantum mechanics to finally knit them together. That's a long way of saying, I think a lot of our colleagues have voted with their feet or their pencils and their computer simulations to say they think the quantum weirdness is at root. That's probably not going to go away. And we got to keep working on how to get other parts of our description of nature to fit more into that kind of picture.